My name is Jeff Kember. We're going to be talking about high-performance file storage. I've been at Google about 2.5 years now. I'm a technical director for media in the office of the CTO. So cloud storage, it's a really complicated thing for some people when they come and talk with us about it. They're like, wait, there's a couple different options. How does all this work? So Google has a ton of compute, and they also have a lot of storage, and they try and keep it really separated into just two simple areas. The Google Cloud Storage that you'll be running on when you run on Google Cloud Platform is the same technology that Google runs all the rest of its infrastructure on. I think that's kind of the important thing, is that we don't have a separate version for enterprise and a separate version for Google. We just have the one version that is Google scale. So oftentimes we talk about object store. If you want to bring many, many hundreds of petabytes or exabytes to us, object store is obviously where you want to put it. There's other interesting use cases, though, that take advantage of our persistent disk, and we have a hard drive variant as well as an SSD variant. You'll find it's called just PD for short, or PD SSD, to make the distinction for ultra-low latency. We also have local SSD. So the distinction here is persistent disk is attached, it's network attached, I should say, and striped, and can be up to 64 terabytes, and expect that to grow. Local SSD is up to 3 terabytes, and that's physically attached to the machine. In terms of our object store, the cool thing is we have a couple different flavors of it. So multi-regional allows you to be able to store data in two locations that are more than 150 miles apart. And that's compelling in the fact that Google has a private network. We'll talk about it a little bit later, as well as we have dedicated lines under the oceans and between the data centers. So multi-regional is really fantastic for content serving. Regional is interesting in the fact that for the highest performance, the data is stored in the data center that you're performing the compute operations on. It's also slightly more economical. Nearline is our storage for data that you want to access sometime in the next year. And if the data is going to sit as in an LTO replacement, then Coldline is the appropriate option for that. So the cool thing with multi-regional is the fact that it is priced at the same price point as our previous version, except you get the multi-regional aspect included in that price. So if you want to do content serving and use either RCDN or use Akamai or use Fastly, then you're serving from multiple locations, so you're going to be in a scenario where your latency is reduced further. Simple API. These are commands that are going to allow you to create a bucket, either a Nearline bucket or a regional bucket, and then you can read an image from either of those. It's the same API across all of our storage, and we're really proud of the fact that you don't have to be using different systems to be able to access it. In terms of pricing, as I mentioned, it's really inexpensive to use multi-regional as well as regional. In terms of reads and writes, we've priced it so that you can almost make, you're able to do production level reads with it without having to pay additional fees. You can see it's 4 cents per 10,000 operations. So it's highly performant, and you can see that we have 11 nines of durability. That level of durability is consistent across our entire storage offering. So for regional, for many media customers that I work with, regional is sufficient if they're not serving content. It's optimal in the fact that you're committing a write to that data center. You don't have to wait for 2 writes to occur in 2 different data centers. It all just happens right there within that zone and within that region. So it's highly performant, and at the same time, you only pay for it as you use it. So Nearline was brought out as our original LTO tape replacement, and you can even serve content from Nearline or Coldline, which is interesting in the fact that it's same couple of milliseconds at most, typically less than that, access time for any of these platforms. With Nearline, you can work out the pricing such that if you're going to read the data in less than a year, Nearline makes sense. We have a tool that automatically ages the data off so that if you wish to enable it, you can take the data from regional and then move it to Nearline, and then move it to Coldline over time automatically. From a performance standpoint, we came up with an SLA that was several seconds of access time, and this is in contrast to previous offerings that, from other vendors that may have been several hours in access time and requiring a different API. So the opportunity to have Nearline available to you in a millisecond capacity we're really excited about that. And that enabled the opportunity to have Coldline available. And for us, we typically advise people, if you're not going to read the data in a year, put it on Coldline. Both Nearline and Coldline have a 1 month, 30-day requirement in terms of cost. The multi-regional and regional are just as you use them. Again, consistent API, you can see that we're using the same get-put commands that you saw earlier. And the comment about serving the data, performance-wise, it'll do that. Cost-wise, we feel it's a better option for you to be able to move it to another tier, which you can do on a per-object basis. So this is a little bit more of a breakdown here. You can see on the left-hand side, there's no minimum storage duration. On the right-hand side, we do a 30 and then a 90-day. So it's really intended to be more for, as you move toward the right, more for longer term. We have quite a few customers who are contractually obligated to store 3 copies of data. And in that context, they've now started moving to storing 2 copies of LTO tape and 1 on Google Cloud. And a number of them have now gone to 1 copy of LTO tape and cloud, and they're finding that they're not restoring from tape on-prem. The tapes are going off for off-site storage, and they're restoring from Google Cloud because they can get it back in milliseconds and only restore the objects they need, as opposed to restoring, online an entire LTO tape, which takes time in the robot and such. So if you want to use them all together, the cool part, as I mentioned, you can do. We announced this when we announced Coldline, but we didn't really get a lot of fanfare. The idea of having the ability to have multiple objects in a bucket and being able to control which category each object is in. And that really helps from a cost and performance standpoint, because you're in a scenario where you can say, I have this 17 petabyte archive and 50 terabytes of it I'm going to be using, so I'd like to have that available to me at a higher an easier read costs, let's say, and you put that in regional. And then you can have another portion of that available in multi-regional, because that's content that's finished, final, and you want to be able to serve that content. This also mentions the data lifecycle, the ability to move easily between in an automated fashion. So when moving to block storage, we have persistent disk, which I mentioned earlier. So the machines boot. When you fire up a VM, you get persistent HDD, so just standard PD, and it performs well. It's our boot disk. Quite a few customers use that. It's inexpensive, network attached. The opportunity to move to SSD for PD is also compelling. We have a single node filer, which I'll talk about in a few minutes, that's backed by both local SSD, essentially as a RAM replacement, in addition to onboard RAM. But it has persistent SSD on it for, again, high performance. We're looking at 64 terabytes again, but we can increase that on the PD. So local SSD, these are 3 different use cases that I brought up as examples. So a VIR is a on-premise physical box, and that's what people are most used to. They also have a cloud variant, which is called a VFXT, and it's quite a bit different than the on-premise box. What's interesting about it is it's the same algorithm, but it's highly scalable. It's your cache and your file system together. And the advantage of being able to run that on the cloud is you start with 3 nodes and you can scale up to 30 or 50. You get the high throughput that we have on our machines, currently 16 gig per VM on a 40 gig interconnect. And that's all software-defined networking, so we're able to maintain that line rate as you scale out. With the VFXT, you can run it on PD SSD, as I mentioned, or if you wish, you can run it on local SSD. When you run it on local SSD, you get a couple cool things happening. 2x performance across the board increase, and for random reads, which for many media customers or people doing high computational loads, it's a lot of random reads. You get a 4.5 times speed improvement because there's no network I/O required to go to the network attached storage to get at your data. It's just sitting there, already ready to go. For transcoding, I have customers who will go use FFmpeg, grab the data, put it on a machine with local SSD, have the mezzanine file there, do a transcode to 27 different flavors of codecs and resolutions and bit rates, spit them all out onto local SSD, and then copy it over when it's done. They don't even have to set up a file system. So that's, I think, a highly useful use case. It's also available in small chunks, 375 up to 3 terabytes. For simulation, which Adrian is going to chat about in a couple of minutes here, simulation is exciting in the fact that you can do fluid simulation, you can do destruction work. In the same simulation idea, you can also do finite element analysis with car crashing simulation, for instance, using our GPUs if you choose. All of this can make use of our local SSD for ultra-high speed storage, and you can supplement that with a cloud file system as well. This is a slightly complicated and barely legible graph, it looks like, of hybrid rendering. What we have on the left-hand side of the screen is an on-premises display, and on the right-hand side we have the cloud. So really what we're talking about here is there's a file server, there's asset management, there's licensing, there's all the normal things you would need to be able to make a picture in this diagram. On the right-hand side, we have the cloud equivalent of that. So if you wish, you can point back on-prem across an interconnect, VPN, however you wish to configure with us. Then you can point back on-prem to get access to your asset management and your cloud license server. What's interesting about this for me is if you remove the license server component and you change out the compute VMs as being standard compute VMs and change them for GPUs, I would change the word rendering to oil and gas. Or if you decided that you wanted to run a very large amount of compute, like 100,000 cores, for instance, and you wanted to do financial simulation work, I would change the word oil and gas to financial. The framework looks the same. It doesn't change. We have genomics customers who are using this same framework, and they're able to complete high-performance compute workloads on a per-minute basis on our platform. So in terms of customer use cases, in an enterprise event, we want to be able to tell people, hey, look, we have customers using this. Here are the customers who are excited about the product, and here are the customers who are experiencing great success with it. Most of these customers have come to us and said, we don't want to be in the business of we don't want to run data farms anymore. We don't want to have a huge amount of storage. We wish to supplement the high-speed disk we have locally, but the tier 2, some customers have an object store. The customers who have a large tape robot, they want to be in a scenario where they can start to move off of that. As far as ecosystems go, if you have any of these products on premises currently, you're in a scenario where these are all cloud-enabled to varying degrees. These partners, I should say, form our ecosystem that allows you to be able to extend your current storage directly onto Google Cloud in a fully managed fashion. And in terms of partners, I mentioned Avir earlier. We also partner with PixCache out of the UK. NetApp is listed on here. These are, again, fantastic opportunities to be able to take brands that you know, love, and use currently and be able to just extend the product that you have. In terms of our backbone, you can see we have a whole lot of lines on this graph. The opportunity to expand this, it's depicted in 2018, we're adding additional undersea links. You'll notice there's multiple links as well. I meet customers who are under the impression from our marketing information that we only have kind of single links under the oceans. We have multiple paths, and we're the only cloud provider on the planet that has a private global network. So in this depiction, you can jump on in Helsinki and then jump off in Taiwan or New York or back in Tokyo or Sydney. And in that scenario, you're on our private network the entire time. So it's all software-defined networking. We have our own quality of service. We're in a scenario where it's encrypted in motion and at rest on our storage. From a peering standpoint, we have over 100 peering sites. So if you're with Equinix or other, there's a high likelihood that you can run fiber directly into our switch and have a direct connect with us. Talk with us about those opportunities. We have a roadmap. We're offering new opportunities in that area over time. But the opportunity to be able to be near one of our POPs, pretty much in most major cities on the planet where there's fiber peering, we're already in that colo. From a machine learning standpoint, this is an area that we're really excited about in terms of what can this do for financial, media customers, retail. What's excited for me about machine learning is the fact that it's prevalent across our entire product line, and Google has gone to the trouble of building TPUs, which are TensorFlow processing units. So that gives us the ability to run on custom hardware at extremely high speeds. That was the engine that was powering the AlphaGo competition that Google won last year. What this means to you, though, is normally you do your training on CPU or GPU, and then you deploy on that. However, with TensorFlow units, you can get another order of magnitude, typically, faster processing. And you can see we've announced Cloud ML Engine. We can talk more about that in other sessions. But you can see we have an option to go with open source TensorFlow, and you can run that on any cloud you wish, on your local laptop or data center. You can take those same graphs you've made and also run them on Google. So like our container engine, it's a highly portable, open source machine learning technology. The ML APIs are TensorFlow, but with our models already trained and ready to run on them. The cool part with that is that you get our 100 languages and translate, you get our video and now vision, I should clarify, vision and now video API. We announced the video API yesterday as general availability. And the exciting part about that is it's the Vision API on wheels. So you can feed it large movie clips, it'll generate metadata for you, and it'll do logo detection, and it will allow you to do optical character reading, and it will tell you where in the world the scene is, if it can identify landmarks and such. I urge people, if they want to play with this, to download Google Photos. It's a free app for Android and iOS. And the cool thing with it is that it's a really nice intro to how our machine learning works for imagery. You put it on your phone, give it access to your photos, it pushes them to the cloud, performs the ML, and then provides that data back to you. But you don't see the outcome of it. You just are able to type in search. You can type in dog, and you can get all the dogs in your photographs. But if you type in husky, Adrian's dog will pop up on the screen as he has a husky. So it's a nice way to kind of go, well, that's actually kind of cool. That'll give you an opportunity to see what the API can do in an application setting. The APIs are available for anyone to use. You can also, in concert with that, work with your custom model. So in terms of that, the normal process is working with a training workflow. And then we've announced today, this morning, I believe, data prep, which provides you the opportunity to be able to simplify the machine learning training process for you as far as preparing your data in a more accessible fashion for you as a user to be able to train your models. The prediction flow is depicted below, and that enables you to be able to actually run the model that you've trained. So with that said, I'd like to invite Adrian Graham up on stage to talk with us about simulation for media. Thanks, man.
Grazie, grazie. Everybody can hear me? Good. Ooh, I've got a clicker forward and back. So my name is Adrian Graham. I'm a cloud solutions architect out of the Venice office, which is Venice, California, not Venice, Italy. The food is pretty good at the office still, but so my background is I come from the visual effects world. I spent 20 years working at companies like Industrial Light and Magic and Double Negative in London and Digital Domain in Venice, which is actually where the Google office is now. But one of my focuses, foci, if you will, was on simulation. And simulation is a good practical application for how we deal with storage on any platform, local or on cloud. There's many challenges. And if you think about what a simulation artist who's going to do a fluid dynamic simulation, for example, they need a monster machine with a ton of CPUs, maybe GPUs if you've got GPU acceleration. Massive amounts of RAM, because once you generate the data, you want to read it back in and hold it in memory so that you can scrub back and forth. And obviously, there's a lot of disk required. The data that you're generating is on a per frame basis, and you're generating data for things in a fluid simulation like the liquid and the foam and the spray and the mist, and all those are on a per frame basis, and they could be thousands, tens of thousands, millions, or hundreds of millions of elements. So what do you do with all this data? How do you manage it? And in that realm, we're talking about a production problem where you've got multiple iterations of the same effect. And I'm going to use this story from my old days back at Digital Domain. We worked in this production on this commercial for a video game called The Darkness. I can't speak to the quality of the game, but we had to create these very sinewy, fluidy, smoky elements that this character could control. And we used a tool called Krakatoa. Krakatoa is a way, it's almost a pipeline for generating simulation. And the workflow is such that you generate one simulation, and then you run that simulation hundreds or thousands of times, each with a different random seed to generate slight variations. And then you can take all those sims as a single element, and then you can combine them and render them as one. And that allows you to create this long, sinewy, smoky effect. Now that's just one element. These shots might have 8, 10, 20, 30 elements in them, and they're written on a per frame basis. So when you think about you need thousands of passes for each element. A shot might be 240 frames. Remembering we don't render to movie files. We render on a per frame basis. A 10-second shot is 240 frames. So when you add all that up, my example at the bottom here, the end of the story is that I got a visit from the senior system admin telling me that I was using exactly 43% of all storage at the facility. That was, and this is one take of one effect. So that is a huge problem. So, which leads me to the next slide. Because when we only have one take, what do we do if we want to generate multiple takes? What if the supervisor says, that's great, but make it blow up a little more here, or make it move a little faster? And instead of just running one simulation, you want to run a whole bunch of them, each with tiny variations, so that the supervisor can look and say, I like that one and I like that one, go in the middle of that. A good example here is the wedge of this fluid dynamic simulation. I'm only changing one attribute, and that's this max voxel size, which is essentially the resolution of the simulation. But you could see tweaking one tiny little value exponentially changes the outcome. 25 million voxels from 226,000 from changing one value. So what this means is that you could, what if we could run all three at the same time and then view them at the same time and be able to choose? And this is just one attribute. You need to be able to, these numbers are not necessarily all normalized, so you've got all different attributes that require all different kinds of inputs and ideas as to how to run them. So, put it on the cloud. So let's talk about how, real quick, how I did that simulation. That was a real quick and dirty simulation that you saw a couple slides ago. I did it 2 days ago within a couple hours on the cloud. But if we want to get a little bit technical here, if I may, we've got a couple scripts that we're running. We're running a proprietary script that runs inside of Maya. We're using Maya Bifrost, which is a fluid dynamic simulation engine inside of a product called Maya by Autodesk. It's got a proprietary scripting format called MEL, which is very C-like. And there's a tiny little snippet here. All it's doing is saying, list over all the fluid containers, and for each container, write out the data that it's generating. That, in turn, is controlled by a Python script, which takes in, that's your UI, that's your front end. And this is all command line. We're not doing anything fancy, and I'll show you how what the architectural diagram for this looks like. But essentially, it's taking a start frame and an end frame and a variable value and an out directory, and that's it. So if we look at what the command line, an example of two wedging command lines might be, in this case, we've got max voxel size, or MVS, of 0.05 and 0.001, and I would run these two separate commands on two separate VMs. So I can spin up a managed instance group with as many as I want, and I could deploy one sim to each group, or sorry, one sim to each VM in the group. What do we do with all this data? Hope everybody gets the Seinfeld reference there. So once we've got our chosen effect, and we've got the magic numbers, and we've got an idea of exactly where we want to go, the output is going to be the base simulation. So we run it at the full resolution of whatever settings we want, but we're not done. We got to mesh that. And meshing is a whole separate, it's not a simulation, but it's a procedure that runs on the simulation data to surface it. And from there, we might want to generate foam and mist and spray and bubbles. And those are all separate simulations. And all those simulations generate data. And how does it generate data? It rams every CPU on the box and spits out massive, massive amounts of data, which is ideal for local SSD, for example. Up to 3 terabytes in storage, what is it, 700,000 IOPS. It will absorb that data in the blink of an eye with no problem, and you won't get a visit from your local sysadmin. And then once you're done with all the simulation, you want to perform rendering. And that is actually the subject of a talk that I gave a couple hours ago on rendering in the cloud and running a remote display over Teradici, which I'll talk about in a second. So quite simply, the setup that I use to run all this is extremely simple. I just have I only had one VM in the cloud, but I'm using my local workstation, which is just my Mac running Maya. And I saved out the file. I used gsutil to copy the files over, and I just ran a shell on the remote machine. I actually have a license server. That's another problem. You got to deal with licenses, but you need to license the software. So I'm running a license server on the cloud with feeding a license to the remote display, or sorry, to the remote machine as well as to my own machine. This is what Jeff showed earlier. It's a little more legible, but it's an extremely detailed layout of how an entire visual effects pipeline might be built in the cloud. If you want to see more of this, if you want to talk about this, come see us at the Frigitecture downstairs, and we can actually lay this out and talk about it using these little fridge magnets. I hope everybody's seen it. It's a lot of fun. Now, what I showed earlier, and I think it was recorded, so you could watch it later, is I did a remote desktop session into the cloud. So I didn't even have local capabilities. I was using I was going over Teradici PC over IP, which is a protocol for remote desktop by a company called Teradici, and I'm running, in this case, a Windows box on in the U.S. Central, U.S. Central data center, which is about 1,500 miles away, and the ping time was about 40 milliseconds round trip. Pretty amazing what's going on here because we were rendering on 128 GPUs, 128 K80s. So in all, thinking about the powerhouse that we have available to us in the cloud, or how we could build a powerhouse, a 64-core machine, nobody is going to buy you one of those at your, if you work in visual effects. But the fact that we can have almost a half a terabyte of RAM in the visual effects world is unbelievable. And at 80 cents an hour, you can't beat that. And you can, of course, attach up to 3 terabytes of local SSD or PDSSD. Compute GPUs, there's also a number of renderers that are running on the GPU. There's Redshift and V-Ray RT and that type of stuff. And the throughput is pretty amazing, up to 16 gigabits per second. Within a zone, it's this demo, I urge you to go look at it once it's posted online, is that we've got this massive scene that is rendering on those 128 GPUs, and on my local Windows remote instance, not local, but remote instance, I'm tumbling in almost real time, and it's resolving in less than 5 seconds. So with that, we're going to hand the aluminum pole over to Mike Warren. Let me unlock it for you.
Thanks, Adrian. I wanted to start with a little bit about myself. I have a PhD in astrophysics, and my PhD was simulating the universe, the dark matter in the universe, using initially 1 million particles. So over the span of my graduate school career to about 3 years ago, those simulations with the same software went from 1 million particles to 1 trillion particles. So about a factor of 1 million in scale and about that same factor in computing performance. And that came from Moore's law combined with the scaling in parallel machines. And kind of in the midst of that, the popularity of parallel machines got to the point where we couldn't get time on our local supercomputer anymore, so we started building our own machines. So you see me there on the cover of Linux Journal with a cluster of 16 PCs running Intel processors connected with Ethernet. A very normal architecture these days, but this is 20 years ago. So we've been working in this same sort of environment that would be completely familiar to someone logging in the command line of a Google Compute node, and we've kind of been living in that world for the last 20 years or so. So Descartes Labs was founded just a little over 2 years ago. Scientists from Los Alamos. We've doubled in size twice now to almost 30 people. We've now got an office here in San Francisco and another one in New York City. And I want to talk about today kind of one of the problems that we ran into as Descartes Labs and what we did to solve it. And then at the end, I want to do a demo of one of our products that we just released earlier this week on Tuesday, which we call GeoVisual Search. So one of the key reasons we thought Descartes Labs was a good fit as a startup is that satellites produce a lot of data. This is an image we made out of Landsat 8 data. Kind of an endless summer day on the surface of the Earth. The Earth has never looked like this. It requires quite a lot of processing to get rid of all the clouds and artifacts and other things. But it makes a nice picture to look at. But you can't really appreciate from this image the fact that there's underneath this about 320 terabytes of data that had to be processed in order to make this image that you can zoom into any part of by a factor of 1,000. So I was going to use a quote from Ken Batcher here about I/O-bound problems, but the lawyer said that would violate copyright. So I'm quoting myself from a few years ago. A supercomputer is a device for storing obsolete software libraries. And this is kind of to point out the difference between traditional HPC and the cloud. You run something on an HPC machine, those libraries just stick around forever. The Fortran matrix multiplies that seem to never die are going to be on every one of those machines. And at Descartes, we started fresh, knowing that the cloud was going to be the future. And you can see that today, the fact that Intel came first to Google with Skylake, not the national laboratories that had traditionally been the leaders in supercomputing. So what was the problem we ran into? And it's a core part of the Unix philosophy that everything is a file. So the cloud does a lot of things that are really helpful, but one of the things it doesn't do is make architecting and developing application software easier. So object storage, anything you stick in gs:// does not conform to the everything is a file interface, and it breaks a great many things. So the traditional POSIX interface to a file is open, read, seek, write, close. You can't do any of those things on an object in Google Storage. You instead have a RESTful interface through HTTP doing get and put. And you don't have a file system hierarchy with directories. Each object is labeled with a globally unique identifier. So one of the things you can do with a file is update a block inside that file without changing the rest of the data. But in an object store, if you change one bit in that object, you rewrite the entire object. So those constraints are there for a reason. It makes object storage much more scalable and much less expensive. But the cost that you do have to pay is modifying code that already exists to work with an object store rather than a file system. So to give you an idea of kind of the relative importance of these different interfaces, we used Google BigQuery with the public GitHub repo database and ran this SQL query to show how often these various interfaces show up in the code on GitHub. So fopen showed up about 740,000 times. All of the rest of these interfaces are less than 10% of that. So 90% of the code out there is going to be using a POSIX interface and expect a file system. So how do you match these two APIs together? Well, the typical approach is you copy things from object storage to a local file using the persistent disks that Jeff talked about. So if you've got relatively small files, making a copy in the local storage works pretty well. You do a GeoVisual copy, it shows up in your local file system, and then your application can read that data in. And that second read is actually very fast because that data is coming from memory, because the operating system is clever and caches all of that data in the buffer cache. But when we get to larger files and higher data rates, we're going to run into some restrictions because a PD hard drive has a limit of about 180 megabytes per second of read bandwidth and 120 megabytes a second of write bandwidth. The object store can actually provide data much faster than that, but you can't ingest it and write it to the disk at those rates. Although if you paid attention today, Google announced with SSDs, you can now configure machines with a PD SSD with something like 800 megabytes of read bandwidth on your node. So in what is often the ideal situation, if your files can fit in less than about half the memory of the machine, you just set up a RAM disk and read the files from object storage into that RAM disk. It never runs into any of these restrictions, and in fact, you then don't need a local disk at all. You can also try to rewrite your code and not deal with a file system at all. Go directly from the object store into memory. We like to do this with Python, where you can actually do a GSUtil cat on the object through a pipe, and then Python can redirect that pipe into a memory buffer, which you can pass off to your application code. But one of the downsides of this is now that that data is in your application memory, and it can't be shared by other processes that may be running on that machine. And that's very much unlike the file system, which can share data to multiple processes out of the buffer cache. And it's actually fairly hard to write interfaces like that, because a lot of application codes are going to want a file pointer or a file name, and you have to dig down into the guts of the code to actually find the memory buffer that you want access to. So finally, object storage just isn't an option. If you've got very large files, hundreds of gigabytes, which are bigger than the memory of the machine, that you need random access to, there's nothing you can do apart from the former solutions, which are often very slow of reading to local disk. So what you really want to do is actually put a virtual file system on top of the object store. And the Linux operating system has supported that for a long time through the virtual file system that they call Fuse. And here you can see the first commit in Festivus was January 22, 2016, so it's just a bit over a year old. But why did we write this code ourselves? Isn't this an important enough problem that there are lots of open source solutions? So we tried all the solutions we could find. There's GCS Fuse, S3FS, a number of others, but none of them performed at the level that we required. And the reasons were they were just slow at reading, and they handled the metadata very slowly in terms of figuring out what files were, what their modification dates were. So what is Festivus? It uses the asynchronous API of libfuse in the Linux kernel. The kernel does callbacks to this user space code. When you do a system call like open in the kernel, it knows to talk to the fuse module, calling the open stub inside of that code, and doing the right thing over HTTP to the object store. And rather than talk to the object store for metadata, which is often very slow, we just put all of that in a separate in-memory key value store, so we can access that with very low latency. So a very important optimization in all of this is actually modifying the Linux kernel. As some of these parameters in the kernel have been set specifically with disks in mind, where a block size is 4 kilobytes and latency is typically below 10 milliseconds. And now we're talking over the network, and we can read 4 megabytes in about the same time as it takes to read 4 kilobytes. So we want to increase the kernel parameter for the maximum number of pages per request from the default of 32, which limits the size of the read requests you can make to the object store of 128 kilobytes to a much larger value, so you can actually do requests at 4 megabytes. So since that requires a kernel update, we have to deploy all our systems with a modified kernel. And if you're somewhere where you don't have control over the kernel, you won't be able to do this. If you're working in Kubernetes and the kernel hasn't been configured with this parameter, you can't access this increased performance. So how does it measure up? So we can see the first table, we're looking at the bandwidth in gigabytes per second on different node types initially, and then different numbers of nodes reading in parallel to the file system. So the bottom line there is 231 gigabytes per second of I/O bandwidth. Now that's an impressive number even at a supercomputer center where you've spent tens of millions of dollars on your Lustre file system. In fact, you've spent so much money on that file system, you don't let people store files there persistently. It's mostly a scratch disk that has a fixed time. But this bandwidth is going to normal multi-region Google storage, so it's reliable, it's scalable, it's persistent. So it's exactly what we want for a high-performance file system. The other table shows sort of the performance versus GCS Fuse, which is an open source implementation of what sort of performance you get if you're doing random reads in a file, where you can't depend on prefetching to give you better performance. So you can see that if you typically read something like 1 megabyte blocks, Festivus is giving you 270 megabytes per second versus GCS Fuse is down more than a factor of 20 from that. And for very large blocks, we're basically up at the network limit of the node at almost 1,600 megabytes a second. So a question for you is, what's next for Festivus? It does what we want it to do at Descartes Labs, but is it useful beyond our application? And we're a startup. We didn't intend to write a file system for other people to use. We've got other things that keep us very busy. So what we have done is we published a paper about this. So if you're motivated, you ought to be able to follow along and implement something similar for your own use case. Could this be a viable commercial product? I don't know what the market is for a Fuse file system. on top of object store. Would we be better off just open sourcing it and letting the community take over and take it where they will? And if you're not really sensitive to performance, you can use one of the other open source implementations. It does the same things, just not as quickly. So now for the Festivus miracles, what does this file system enable us to do? And I'll go through a couple slides here kind of describing the demo I'm going to show you. But if you like, you can follow along. These are publicly released maps at maps.descarteslabs.com and our GeoVisual search at search.descarteslabs.com. So first, maps. Now, everyone's used to Google Maps Earth layer, where you can scroll around and zoom in and out on the world. And we've done something similar in the visual bands with Landsat 8, which doesn't go to as high resolution. It's limited to 15 meters per pixel. And this was collected from about 4 years of data from the Landsat 8 satellite. But beyond the normal visual bands, there are some newer satellites that collect information in very different ways. So in the middle there you see Sentinel-1, which uses synthetic aperture radar. So it shoots down microwaves at the Earth and measures what gets reflected back. So it can see through clouds, and it can detect things that are very difficult to detect in normal light. Finally, Sentinel-2 is the European Space Agency's satellite, which also has normal visual bands, but in addition has a set of bands that are just beyond the visual into the near infrared, which are very sensitive at classifying different types of plants. So that's in the region where the chlorophyll or the cells in the leaves of the plants become very reflective in the near infrared. So you're not just limited to a normal map, you can look across all of these bands. And this is just an example of what the synthetic aperture radar looks like in this area, where the bright yellow shows strong reflections, often vertical buildings. If you look carefully a little bit to the east of San Francisco there, you can see some spots in the water, and those are actually where ships tend to anchor themselves and have created enough of a signal over the average of all these images that were put together to show that pattern of where the ships are anchored. And then the demo I'll show you now is called GeoVisual Search, where we divide the Earth's surface into billions of tiny images, and we extract a visual feature vector. And this was done using Google Cloud, using TensorFlow on Google Cloud. And once we have those feature vectors, we then need a way to search them very quickly so that when someone clicks on a particular type of object, we can search through all these billion images for the 1,000 images that look the most like that. So if we can switch over to the demo. So this is our map of the United States. We can zoom in and out. We've done some sort of preset searches. This was a waste treatment plant, which is just south of Los Angeles Airport. But I'm not going to use that one. I'm going to go up here And you can see this is one of the big parking lots near LAX. So I'm going to click that, and in that amount of time, it's found the 402 closest matches across the United States, and showing you up on this map where they are. And down here, we see the image chips from each of those matches, and you can see it's done a very good job in finding those parking lots. So we can go up here and check some of these other points to see, are they really parking lots? There's one, it was a parking lot. We can go up here to North Dakota. Turns out this is not actually a parking lot, but it's a junkyard of cars parked next to each other. So that's just pointing out that it's GeoVisual search. It's things that look similar, and you would need other layers to go beyond that for very sophisticated searches. We can do another one here just of these wind turbines. So there, you can see these kind of cluster in the middle of the country where it's windy. But again, we can go and check our accuracy. Here's some more wind turbines. So if you'd like to play with that yourself, just go to search.descarteslabs.com. Reserve yourself some time because it's fairly addictive. So to wrap up, I wanted to talk a little bit about the Descartes Labs platform. So what we've done is taken data from all the public satellites. We're a partner with Planet. Will Kirkpatrick is going to be giving part of the keynote tomorrow morning. Today they announced they'd moved 7 petabytes of their data into Google Cloud and are now going to be distributing all of their imagery from GCP. So our platform is intended to get rid of a lot of the friction that people deal with these massive satellite data sets. So we have a very simple Python API which allows you to query and retrieve raster imagery across sensors, spectral bands, time. You can leverage the whole ecosystem of cloud tools on this imagery however you would like. We leverage the cloud to be able to scale jobs up to thousands of nodes. This is a closed beta now. If you're interested, please contact us, hello@descarteslabs.com. Later this summer, it will become more open. So finally, if you'd like to learn more, the paper I mentioned earlier, the link is there. We have a technical blog post on Medium describing GeoVisual search at our homepage, descarteslabs.com. We're hiring, so if you love to work on problems that are really cutting edge and can help a lot of people, let us know. Thank you.
Really want to thank Mike for being here today. Fantastic presentation, and Adrian as well. Excellent. Thank you for coming. We'll have a few minutes for questions. There's microphones in the center as well as on the other side of the room. This is a great opportunity to ask questions. Please come up and let us know what your thoughts are.